Hello again, and welcome to another final exam review session for Calculus 3208 presented by CDLI. And today we're going to talk about derivatives again, but this time we're going to get sort of more general about the idea of a derivative. Previously we talked about the derivative as the slope of a tangent at a particular point. Today we're going to talk about the derivative as a function itself. And what does that really even mean? So let's get down to business. First thing we see here is that we have our first focus will be on the definition of the derivative function as opposed to the definition of the derivative at a point, which we saw earlier. Then we're going to talk about the meaning of the derivative, so what does the derivative mean? And then we'll talk about computing derivative equations, so getting an actual equation for a derivative function using our definition of the derivative. Alrighty. So what we start with here is we have an example that's sort of pre-worked out for you, and I just sort of want to do a quick kind of comparison type analysis on this stuff here. So it says right here that we're starting with some function f of x equals this quadratic x squared plus 7. And it says, well, what happens if we want to find specifically for one point where x equals a, the derivative or the slope of a tangent line that touches that function? Well, we've seen this formula before. This was our limit and difference quotient definition of the derivative. So if we choose a point where or a value for a where we want to find that slope of a tangent, so we'll say at x equals 2, then what we do is we fill all of the stuff from here, we take that formula and we rewrite it just with 2 instead of a, because that's our point now, and then we use this particular equation that we know for our function to get f of 2 plus h starting off minus f of 2. And then we go through all the algebra, and we looked at several examples of this in a previous video. But we go through all the algebra required, and what we find out in the end is that our limit has a value of 4. So we know that the slope of the tangent line that touches that curve when x equals 2 is 4. All right. What does it mean if we want to talk about, instead of the derivative as a number, like a slope, what is the derivative as a function? Well, generally, for any value of x, instead of saying specifically for one value, like we had 2 over here, and we generally usually say a as a placeholder until we pick our number, what if we don't want to say a specific value to start off with? We just want to find the derivative, and we want to be able to run through our whole limit process, and instead of just come up with a number, we want to come up with like a formula. A formula so that I wouldn't have to use that limit process over and over and over again if I had to find the slope of my tangent at several points. That's one way to look at it. So what we do is, instead of taking a number like 2 as we did over here, we're just going to leave it as x for now. And remember that the value of x that we choose could be the tangent at any point, so x is not dependent on this value of h. So we just leave it as x, and we sort of treat x as a constant in terms of our limit. It's not a constant, it's still a variable, but in terms of our limit, it's not affected by h approaching 0. So we treat it as a constant for our limit. All right, so you'll notice that the process that we went through over here and the process that we go through over here for actually evaluating that limit are identical until we get down to this one spot right here where we have 4, and here we have 2x instead. And so when h approaches 0, we're just left with an answer of 2x. So what we would say for this particular function is that we go through all that work, and now we can say that f prime of any value of x is equal to 2x. So if I wanted to find the slope of the tangent now for that particular function x squared plus 7, at any point at all, I don't have to redo my limit process. I can just fill it into this formula. So let's check the one that we already had done. When x equals 2, this should tell us that the derivative f prime of 2 would be 2 by 2. Oops, 2 by 2, which is equal to 4. So the slope of that tangent is exactly what we predicted over here. But if I wanted to pick another value, like let's say -1, I don't have to go through the whole process again. I just plug it in there, and I've got -2 without having to calculate any limits. So when we talk about the derivative as a function, one thing we can say about that is it's kind of like a formula for the slope of the tangent at any value of x instead of at a particular value of x. Okay, let's move on. Now, it says we're going to talk a bit here about the meaning of the derivative. So we have lots of different words that we use to describe derivatives. So we can call it a derivative function, like we just saw. And in the words that we already used, we could call it a formula for the slope of the tangent at any value of x. So any value of x is the key part there. Remember that the purpose of a derivative and for the slope of a tangent and all that stuff, was it was all about instantaneous rates of change. So this is also a formula for the instantaneous rate of change of the original function f of x at any value of x. And sometimes, since what it does is it tells us the slope of the tangent at any point, we occasionally, or often even, refer to the derivative as the slope function. So notationally, we have a bunch of different ways to write it out as well. We can call it f prime of x or dy over dx. Those are our two most common notations we use to represent a derivative. Sometimes we think of it as the limit as our delta x approaches 0 of our slope delta y over delta x. You might see that occasionally. Or sometimes we, instead of leaving a y out of this, we can say d over dx of f of x. So y and f of x are the same thing, so we can see why that works. And this last notation here, you don't see this very often, but you should be familiar with it in case it crops up at some point. We write a capital D with a subscript of x of the function f of x, and we call that the derivative as well. That's a funny looking one. We don't use it very often, but just in case it crops up, you'll be familiar with it. Okay, so let's do some examples. We're going to find the derivative of a particular function, but notice no value of x is given here. So what we're actually trying to do is find f prime of x without knowing what point we're interested in. We just want to get it generally, so a slope function basically. So we want the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, so that's the limit as h approaches 0. And f of x plus h will be x plus h squared minus 5 times x plus h plus 9. And so all I did there was replaced all my x's with x plus h's. All right, so now I'm going to subtract f of x, which is x squared minus 5x plus 9. Notice I use these parentheses or brackets here because I want to protect all of this because I got to subtract it all. So all those signs are going to have to change eventually. If we don't use those brackets, we sometimes forget to change them. So that's all divided by h now. So this gives us the limit as h approaches 0. X plus h all squared is x squared plus 2xh plus h squared, save you the binomial expansion, 5x minus 5h from the second set of brackets, plus 9, and then we're going to have minus x squared plus 5x and minus 9, and all of that is over h. Now that looks like a big mess, but the nice thing about these is that almost, well, it should be every time we do it actually, every time we do one of these, stuff gets simple in a hurry. So let's see what we can get rid of. Positive x squared and negative x squared are gone. Negative 5x and positive 5x are gone. Minus 9 plus 9, they're gone. And so we have just 3 terms left up top. And if you're doing this correctly, what you will notice is that with the 3 terms that you have left over, every one of them should have at least one h in it. So we've got the limit as h approaches 0, and up top we've got 2xh plus h squared minus 5h, hey, that's an h, all over h. And since everything up top has an h in it, we can then factor out an h, and we'll use that to cancel out the h in the denominator. So this will give us the limit as h approaches 0 of h outside of 2x plus h plus, plus h there, messy handwriting, my goodness, minus 5, and that's all over h again. So those h's, we can just eat those and then get rid of them. And as h approaches 0, all we're left with here will be 2x plus 0 minus 5, and there's our slope function, 2x minus 5. Alrighty, let's try another one. Oh, this one looks like a little more fun. It's got fractions and such in it. So let's go for f prime of x this time. So f prime of x here, it's the same formula every time. Limit as h approaches 0. F of x plus h minus f of x all over h. Okie dokie. So let's fill in some business here. We've got the limit as h approaches 0. So f of x plus h will be 2 outside of x plus h plus 3 divided by x plus h plus 1. And all of that is just this stuff evaluated at x plus h. Then we subtract the original function, which is 2x plus 3 over x plus 1. And we've got that little tiny denominator of h down there. So let's simplify the first fraction we have up there. That one at least can get a little bit nicer. So the limit as h approaches 0 of 2x plus 2h plus 3 all over x plus h plus 1. And let's subtract 2x plus 3 divided by x plus 1. and we're all over h. So this looks pretty disgusting, and it is. But if we try to fill in h equals 0 here, what you will find is it is an indeterminate 0 over 0. So that's not a happy time for us. So what we have to do is we have to try and simplify the expression since it's all rational business. So we're going to go for a common denominator here, and the common denominator we'll try to get for the stuff in the numerator, well, these two don't have any common factors as it stands, so I'm going to have to multiply my second fraction by x plus h plus 1 over x plus h plus 1, and my first fraction by simply x plus h over x plus h on the first fraction. Okay, so it's just kind of scribbling that in there, but I think you're following me. I hope you are anyway. Alrighty. So let's give this a whirl. So this will be the limit as h approaches 0 of, so I'm not going to multiply everything out, am I? Well, definitely not in the denominators, but in the numerators, yep, got to get it all out of there. So I'm going to take all of these three terms times both of those terms. So we'll have 2x squared plus 2xh. Then multiplying by 2h, I'll have another 2xh, and then a 2h squared. And then multiplying by 3, I'll have 3x plus 3h. Okay, and then I have to subtract from that what I get when I multiply these guys together. So that's going to be 2x squared, and then plus 2xh. Oh, I need a bracket there because I'm subtracting all of it. So plus 2xh, and then we have to say plus 2x, and then plus 3x, 3h, and 1. Wow, that's a big numerator. And all of that is divided by the common denominator, x plus 1 times x plus h plus 1. And all of that is still over h, so I'm just going to instead multiply by 1 over h over here on the end. All right, let's see what we can throw away here. So anything we don't want that we're going to try to have for breakfast or something, just to get rid of it. So we've got 2x squared there and 2x squared, and then 2xh here, and then I'm going to be subtracting a 2xh there, so those are gone. And let's see, what else have we got? We've got a 3x here that's being subtracted and a 3x there, so those can go away. And is there anything else kicking around? I did see a mistake I made though. The last term over there should be 3 times 1 is 3, not 1. So that guy should be a 3 there. Alrighty, so we got anything else that's going to cancel? Let's see. I don't see anything else that's going to be eliminated right off the bat there. So okay then, so let's try to collect up all of the things that we have left over here. So if we can do that, I'm just going to put it all up on the top of here. So we're going to have the limit now as h approaches 0. And what's left over in the numerator? We'll have a 2xh and a 2h squared. And oh, look, we forgot to cancel here, a 3h and a 3h. When they're subtracted, they're gone. So I've got 2xh, 2h squared, looks like a 2x and a 3. And then in the denominator, I'm going to have x plus 1 times x plus h plus 1, and an h down there as well. Okay, so we've got all of that business put together. Now, let's see where we're going to go from here. So we're going to have to try and do some fancy factoring with this stuff, I believe.